Hey y'all, here we're going to go through activity 6, which is notes on the electron. I'll be referencing a lot the Hog Hilton Hotel. So if you don't know that or haven't watched that video yet, definitely go back in and watch that. So for a warm-up today, what I was going to ask you to do is draw the electron configuration of an element with 13 electrons and identify what element that is. So if I think back to my Hog Hilton rules and I think about my first floor, my second floor, my third floor with 3 rooms, my fourth floor, and my fifth floor with 3 rooms, I think about labeling that 1s2, 2s2, 2p6, 3s2, 3p6. That should be plenty of rooms for what I need to label. And now I'm going to place my 13 electrons. So I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and that's it. So those are 13 electrons. So this has a 1s2, 2s2, 2p6, 3s2, 3p1 electron configuration, making this element aluminum, which has 13 electrons. So let's get into some of the notes on activity 6. To go over some electron basics that you may have forgotten. An electron is a charged particle with a charge of -1. It has a spin of 1/2 and a very small mass. We normally just call this mass 0. The spin is new to us, and we'll get into this shortly. Electrons have properties of both particles and waves, and an electron is responsible for the chemical properties of an element. The periodic table is set up according to these properties. So according to that, there should be some sort of relationship between the amount of electrons and something's position on the periodic table. This should be kind of familiar to us. If we remember the 2 main models that introduced the electron, first we had Bohr's model, where each ring was like an energy rung, not an orbit or path. And electrons just fit into orbitals' energy levels, and there was a set number of electrons in each level. The modern atomic theory painted a more realistic idea, so let's compare those two. In Bohr's model, we have these energy levels that are almost like rungs to a ladder. And electrons just kind of circled around within those energy levels, and they never really moved around within them. With the nuclear model, or Schrodinger's model, we see that there's kind of a whole cloud where there's multiple different places where we could see electrons existing. And these orbitals may be like here, or they may be like here, or they may be all over the place, but there's different shapes, not just circular paths, that these electrons follow. To get a little bit more into orbitals, scientists use the letter N to refer to the number of energy levels that we've gone down within an element. So for example, 1s2, the number 1 represents the energy level, so N equals 1. 2p6, the letter 2 represents the energy level, so we're in the second energy level. If we think of 3d10, the number 3 represents the energy level. And within each energy level, you're made up of orbitals. And that is represented by a letter. So example 1s2, the orbital is the s orbital. 2p6, the orbital is the p orbital. Orbitals are models of places where you're very likely to find an electron. Each orbital can hold 2 electrons, just like each room can hold 2 pigs. And these orbitals are considered to have different spins, one spinning up, one spinning down. So within this cloud, if we go back to the more realistic model, we have orbitals. So that is to say, if they're in the s orbital, they're likely somewhere shaped like this. If they're in the p orbital, maybe they're somewhere shaped like this. And if they're in the d orbital, maybe they're somewhere shaped like this. And this is a bit of an oversimplification, but it's just saying all of the different places that electrons could be. Let's talk a little bit more about each orbital. Again, within an orbital, the spins have values of 1/2 and 1/2. They're drawn with a half up and a half down arrow like we see there. And the Pauli exclusion principle, which is the first of three rules that we're going to learn, states that no more than 2 electrons can be in the same orbital and they must have opposite spins. We'll come back to that a little bit later. So if we think of our orbital shapes, some helpful things that I like to think of to remember them. The s orbital is shaped like a sphere. The p orbital is shaped like a propeller on a fan, or maybe you want to think of it as a pedal. And the d orbital is kind of shaped like a double dumbbell, 2 dumbbells stacked right on top of one another, fit together so you could carry them a little easier. That's a double dumbbell. Within each orbital, we need to know a little bit about them. First, the s orbital. There's only one s orbital at each energy level. And s orbitals are spherical and fairly simple. At energy level 1, the orbital is called 1s. At energy level 2, the orbital is called 2s. And so on and so forth through n equals 7. So at the 7th energy level, we would have 7s. Let's look at that on the periodic table. These are all our S block elements, this kind of left chunk here in yellow. The only oddball is helium here, so you can kind of just move it over there in your mind's eye. The only reason it's over here is because it's a noble gas, so that's why we keep it over there on the right. But here we have the 1s orbital, the 2s orbital, 3s, 4s, 5s, 6s, all the way down to the 7s orbital. So all of these represent the different orbitals at the different energy levels. As you can see, we could fit 1 electron in the 1s orbital, 1s1, and we'd have hydrogen, or 2 electrons in the 1s orbital, 1s2, and be helium. Similarly, we could say something like 4s2, which would refer to the second electron in the 4s orbital, referring to calcium. 5s1 might refer to rubidium. So each of those things is kind of going to give you an idea about where we can find electrons within the s orbital. The p orbital starts in the second energy level, and there are 3 p orbitals, or 3 rooms. Each of the p orbitals have 2 lobes centered across an axis, kind of like a propeller. The 3 lobes, though this isn't hyper important, stick out along the x-axis, out along the z-axis, so pointing straight towards you, and up along the y-axis. So there's kind of 3 ways, if you imagine this in 3-dimensional space, that it would stick out towards you. The p block of elements is over here and includes our other metals, our metalloids, and our non-metals. And remember, it starts at 2, then goes to 3, 4, 5, and so on. So if I say I'm thinking of something that is 2p1, that's the first element in the 2p block. 3p3 might be the third element in the 3p block. And 6p5 might be the 5th element in the 6p block. So these, just like S, are just aligned with the row it is on the periodic table. The only difference is the p block can hold 6 electrons as opposed to just 2. Next, we have the d orbitals, and this is where we start to get a little complicated. At energy level greater than 2, there are 5 d orbitals, and these orbital shapes get a little crazy as the energy level increases. The d orbital is a double dumbbell, so looking like kind of these guys here in this picture. The d block is our transition metals. As we can see here, there are 10 electrons capable of fitting in that block. The one big difference about the D block compared to the first 2 blocks we talked about, where this is 4s and this is 4p, this is going to be 3d. And the reason is because d orbitals in the 3rd energy level are a little bit energetically higher than electrons in the 4s orbital and just under electrons in the 4p orbital. So that's the reason why, but for the most part, you just need to remember 3d. So d is always 1 behind the row number. But if I say I'm thinking of 3d4, thinking of the 4th element in the d block. If I say I'm thinking of 5d9, I'm thinking of the 9th element in the 5d block. If I say I'm thinking of 4d5, I'm thinking of the 5th element in the 4d period. Okay. Next, we get into our F block. Our F block is a little crazy. It's kind of freaky looking, F for freaky maybe. At every energy level greater than n equals 3, there are 7 F orbitals. And again, they look really crazy. They just look like something like that. The F block is kind of an odd group. It's down here in the lanthanide and actinide series. So if we're to consider something in the F block, there are 14 possible electrons, so 7 rooms or 7 orbitals within the F block. And the thing about F, remember how D was 1 behind? Well, F is 2 behind for the same reasons that D is 1 behind. So this down here is 4F. This is 5F. So we go straight from 7S into 5F over here. So if I say I'm thinking of 5F1, I'd be thinking of thorium. If I say I'm thinking of 4F13, I'd be looking at the 13th element within the 4F block, okay? So that's a little bit about our orbitals. With these, we can use them to write orbital diagrams, which are pictures, and electron configurations, which are words or numerical representations. But we have to follow 3 rules. The Aufbau principle states that as atomic number increases, electrons are added to the orbitals with the lowest energy level first. Kind of like how pigs won't go up the stairs unless they have to. So what that looks like is up here, we've violated the Aufbau principle because this energy level isn't full yet, but we went ahead and filled in an electron here. So this up here is wrong. Down here below, we've done it correctly because we have filled in the 2s orbital before we move on to our 2p orbitals. The next rule is the Pauli exclusion principle, where an orbital can hold a maximum of 2 electrons with opposite spins. So the Pauli exclusion principle states that something like this is correct, but these are wrong because the second orbital there has 2 electrons with the same spins. That's not going to happen. The third rule, Hund's rule, states that electrons fill each orbital evenly before pairing. So pigs will spread out within rooms before they share a room. So Hund's rule states that something like this would happen, but something like this would not happen because we wouldn't see pairing before we've spread out to all rooms like we did in that first thing. Similarly, it says we wouldn't see a down arrow first. We're going to fill in all up arrows and then go in later and fill in all our down arrows. So to summarize those, electrons occupy the orbitals with the lowest energy level first, the Aufbau principle. 2 electrons in the same orbital cannot have the same spin. That's the Pauli exclusion principle. And electrons spread out within an orbital group if they can, which is Hund's rule. The sections of the periodic table can also be used to predict electron configurations for most elements. So let's practice what that looks like, thinking of this as kind of a reference point, where this has gone in for us, and it's really labeled every single element with what its furthest electrons would be. Okay? If I think of boron, it has 5 electrons. So if I were to draw an orbital diagram, I would draw 1, 2, 3, 4, 5. Okay? If I wrote this thing's electron configuration, I would write 1s2, 2s2, 2p1. Okay, and as a note on your packet, your d orbital is missing 1 room. There should be 5. I know there's only 4 on your page. But that's what boron looks like. Okay. Next, let's do oxygen, which has 8. 1, 2, 3, 4, 5, 6, 7, 8. If I were writing this thing's electron configuration, 1s2, 2s2, 2p4. Next, I'll skip ahead to iron, because that's a little bit more of a challenge for us. Iron has 26 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. See how careful I am to follow all the rules, Hund's rule, Aufbau principle, and Pauli exclusion principle as I'm filling those out. So this is the orbital diagram for iron, this drawing here. And if I were to write out the electron configuration, I'd have to write the full big thing, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Okay? Now, when we write electron configurations in the unabbreviated way, we're identifying an endpoint and then writing the electron configuration starting at 1s all the way following through the periodic table. So for example, neon, the 10th element, we have to write 1s2, 2s2, 2p6. It's not enough just to write 2p6. We have to write everything before. When we write something like aluminum, we must write 1s2, 2s2, 2p6, 3s2, 3p1. So again, we're not just writing 3p1, we're writing everything that comes before. With oxygen, we're writing 1s2, 2s2, 2p4. Not just this part, but everything that comes before. Writing unabbreviated or long or full electron configurations can be a bit challenging, especially if we consider writing one for like xenon, where we'd have to go through 1s2, 2s2, 2p6, 3s2, 3p6, so on and so forth, all the way until we got to xenon. That would take quite a while. So there is an abbreviated way to do this called the shorthand or noble gas configuration, where you count the number of electrons, identify your endpoint, but this time you identify the previous noble gas, write the noble gas in brackets, and write the rest of the configuration for your noble gas to that element. So for example, aluminum, instead of writing 1s2, 2s2, 2p6, 3s2, 3p1, which is the full configuration, instead we can find the noble gas before aluminum, which is neon. And neon's electron configuration is 1s2, 2s2, 2p6. So after neon comes the 3s2, 3p1 electrons. So all I have to do for the shorthand notation is the noble gas configuration, where I write neon 3s2, 3p1. This gets even more helpful as you go. For example, atomic number 50, tin, would be the noble gas before that is krypton. And then following that, we have, let's see, 5s2, 4d10 into 5p2 for tin. So I saved myself a ton of time just by writing the noble gas, and then everything that comes after my noble gas until I reach my element. Noble gas configuration can be very helpful. You're not always allowed to use it, so be sure you're following if it's asking you for the unabbreviated or the noble gas configuration, and get lots of practice with both. Lastly, the valence number of electrons can be predicted using the s and p electrons in the highest energy level of an atom. So for example, if we look at calcium, calcium's highest energy level is 4, it's in the 4th row, and it has 2 electrons in the s orbital, no electrons in the p orbital. So it has 2 valence electrons. Sodium has 1 electron in its third energy level in the S, none in the P, so it has 1 valence electron. Nitrogen has 2 electrons in the S orbital, 3 electrons in the P orbital, so it has valence electrons of 5. Potassium is in the same group as sodium, so it's also going to have 1. Be sure you're coming back to these note sets if you need extra practice, particularly with electron configurations and orbital diagrams. The big key here is electron configurations are writing, orbital diagrams are drawing, okay? There will be more videos walking through activities 7 through 9, so if you're still struggling, be sure to watch those. Thanks.